All right, so hopefully you all got my email. That will be doing the quiz on Wednesday instead of today. I just wanted to make sure everybody has a textbook by today or tomorrow at the latest. If you don't, you need to let me know that, but I'm not going to postpone the quiz any longer. It'll still be on Wednesday. Um, it'll cover the first two chapters of the textbook, not anything that I'm covering today. What I'm covering today will be on the second quiz, which will come up in the next week or so. All right. What I want to do to start off today is to review a couple terms from the first chapter. Let me see if I have this here. Let's see if this, yeah, this is it. Okay. All right. So this is section 4, chapter 1. I just want to review a few things from this section as a refresher for some of the things that we'll be doing today. All right. So go over some of these things. Types of data. What you see on your screen now talks about two types of data sets. One of them is called categorical or qualitative data sets, where the observations are categories. They can be written in words. And then we have our numerical or quantitative data sets, where we do math with numbers. All right. Now, the word univariate refers to one variable. So we have a data set with just one variable. It would be called univariate. Two variables would be called bivariate, and more than two variables, multivariate. So if you see those words, you'll know what I'm talking about. So in this case, we're strictly looking at one variable and saying, all right, is it categorical or is it numerical? Should be pretty easy to distinguish between the two types, all right? Because categorical, again, typically words, labels. Numerical, of course, typically are numbers that we can do math with, all right? Okay, so here's an example of a categorical data set where somebody is responding to a question on a questionnaire, all right? So if you could make your college choice over, would you still choose to enroll at your current college? And the choices are DY for definitely yes, PY for probably yes, probably no is PN, and then definitely no is DN. And so the 20, these are some of the responses for 20 of those students. As you could see, pretty easy, right? I mean, these are their answers, right? One student said DY, another said PN, right? So that's a categorical data set. Shouldn't be any question about that, I hope. Okay, any questions? All right, so again, when I use these terms for the rest of the semester, I hope you know exactly what I'm referring to. Again, here's the definition: bivariate, multivariate. These are all in PowerPoints in section 1.4. Two types of numerical: discrete versus continuous. Discrete numerical variables are one where there's a limited number of values, and they could be actually plotted on a number line. And continuous means that there could be any value in between in an interval of values on a number line. So you can have a left endpoint, an endpoint, a right endpoint of an interval. Any values in between those two endpoints would be part of a continuous random variable, a continuous numerical random variable. All right. Okay. So again, just reviews of this. For example, the number of text messages. If this was a data set with 12 students and you were asking how many text messages did they get or send on a particular day. Somebody actually sent 82 in a day. Then this is an example of discrete, right? The number of text messages. It could either be 0, 1, 2, 3, all the way up to whatever the highest you could possibly imagine somebody texting in a particular day. But this is a discrete data set. We wanted to know the time it spent on texting in a day, then that time is continuous, right? 6 minutes, 6.2 minutes, 6.28 minutes. It could be any value in between two values. Anything in, the limitation would be what? The number of decimal points you want to extend the measurement to. So in this case, if you extend it to 10 decimal places, you can get many, many different answers. But the point is that it's any value in between values on a number line. This is continuous. All right. Now, one of the things that we'll be looking at today are bar charts and pie charts, which represent what are called what's called categorical data. All right. And typically, not all the time, but typically, with categorical data, what we're doing is we have various categories. We're counting the number of people who are in those categories. Now, it could be questions on a questionnaire, whatever it might be, but we're just simply counting. There's an exception to that. I'll show that to you in a little bit when we get to chapter 3. So what is a frequency distribution? Frequency means counting. Right? When I say what's the frequency of something occurring, you're counting the number of times that it occurs. So you have various categories, and you're counting the number of people or things in that category. That's what a frequency distribution is, just a list of all the categories and the counts for those. You can express that in a table, all right, with the names of the categories and the counts. You can express it graphically as a bar chart or as a pie chart, all right? So you have choices there. Typically, bar charts and pie charts are for categorical data only, all right? All right. So frequency distribution. Now, frequency, once again, is the count of the number of people or things in a category, number of times it occurs in the data set. That's another way of saying it. Relative frequency, I hope you understand what this means. It means the frequency divided by the total number of observations in the data set. You have a bunch of numbers in a data set, which are the counts, which are measuring, basically the counts in various categories. All right, so the data set might be, somebody might be asked, are you a Republican? Are you a Democrat? All right, are you independent? Are you something else? And maybe those are the 4 categories. So you ask that question, somebody picks one of those 4 categories, somebody else picks another one of those 4 categories, and then once you're done asking everybody in your sample that question, you count the number of people who are Democrats, you count the number of people who are Republicans, you count the number of people who are independent, like that. Those are your frequencies for each category. Find the relative frequency, you would just find, for a particular category, you just take your frequency, the number of people who chose that, being Democrat, for example, and then you divide by the total number of people in the data set. That would be the total number of people you asked the question to in the sample. And that's called a relative frequency. It's a percentage, right? It's a proportion. All right, so hopefully that's clear to everybody what a relative frequency is. And these are things that you would have studied, hopefully, in high school, right? This should have been high school part of math courses. This shouldn't be anything new, but if it is something new, if you, for some reason, they left that out of your curriculum in high school, then you'll learn how to do it now. All right. And here is, again, this has to do with asking people whether they whether they wear a helmet, non-compliant helmet or a compliant helmet when they ride their motorcycles. So you ask a whole bunch of people that question. They're going to choose one of those categories. Then you count them. So in this study, there were 806 people who were asked the question. 250 picked no helmet. 40 said a non-compliant helmet, and then 516 out of the 806 picked compliant. All right. And then you could see that you can express the frequencies, the counts as frequencies, or you can express them as relative frequencies, where you would take each of these numbers and divide by 806 people who asked that in the data set, right? So I hope this is clear to everybody. Pretty straightforward. Any questions about Frequency distribution. This is what a frequency distribution is. You list all the categories, you list the counts of people who are in that category, you count the total number of people in their data set, and then if you want relative frequency, you simply divide the frequency by the total. All right, no questions? Okay, so we'll just move on. Bar charts are one way of expressing a frequency distribution for categorical data. All right. And we'll show you what it looks like. So again, I think I went over this when I went over it last time, but not. If you were going to do it yourself, you draw a horizontal axis, you write the category names below the axis, and then you have bars where the height of the bar for each category is either the frequency or the relative frequency. Right? And again, you can read through this again. I just want to show you, here's that example with the helmets. And here is one way of expressing it is a bar chart, all right, where the frequencies are the heights of each of these bars. Here's the scale for the frequencies. So, 250 or around 250 people said no helmets around. I forgot the exact number. People said they had a non-compliant helmet, and then we had a much, I think 516, I think was the number of people wearing compliant helmets. Right, sometimes what people do when they create these bar charts is they put the numbers right above the bars so you could actually know the exact number. All right, because that's one way of expressing it as a frequency, but you could have relative frequencies over here too. And the bars would look exactly the same with relative frequencies or frequencies. All right, another way now for numerical data, we can use what's called a dot plot. All right, dot plot. So it's a simple way to display numerical data when the data set's reasonably small. Typically, we don't use dot plots with big data sets, but in introductory courses, we introduce you to what a dot plot is. It's a very, very simple thing. Again, what you're going to do is you have a horizontal line as a number line, and you mark it with a scale. Whatever the numbers that are in your numerical whatever your numerical variable is, the various values for it. We go from left, to right, with left being smaller values, right being larger values, just like you would plot any number line. And then whenever you run into a number in your data set, you would just put a dot right above that number on your scale. Right? And if you have more than one value in your data set with that number, you would just stack it. So you put another dot right above the first dot, like that. So I'll show you what it looks like. There's an example right here. Right now, what are we looking at here? Graduation rates for basketball players. All right, so these are percentages from 0. Well, there's no 0 here because everybody let's see, have different graduation rates, but whatever the dots represent. In this case, it runs from 20 up to 100. Each of these dots represents a number in your data set. So there's one value that's 20. There's another value that looks like it's probably around 36. There's another one 40. Another one maybe at 41. There's a whole bunch of people at 100 here. All right. You just count the number of dots. That tells you how many numbers in your data set are the value 100. And you just count them, and it tells you how many there are. So this is a way of expressing graphically the numbers in your data set, numerical values in your data set. All right. And then when you look at it, you can say, all right, now most of the numbers are at 100. There's another large group at 90, maybe 2. I guess it's 92. And there's another one here, and there's a couple of others that have some values in them. All right. So this looks like most of the values are higher values, higher graduation rates, and you have a few that are smaller graduation rates. Okay. See if there's anything else here that I can show you. I think there's more dot plots. Sometimes you can compare dot plots, maybe from 2 different groups. measuring exactly the same thing, two different groups. And you could say something like, well, more people, there seems to be more people who are, for this all group, there's more people who have higher graduation rates than for people who are this other group here. Maybe all represents all student athletes, not just basketball players. BB represents just basketball players. So you can make comparisons here. Most of the values are higher for all the student athletes as compared to basketball players, where it's more spread out. And you can see it's sort of tailing off to the left here with basketball players, and it seems to be more symmetric here for all student athletes. So those are the types of things that you can see. Again, you can have various data sets with dot plots. So anyway, dot plots are used for numeric data as a summary. And then for categorical data, what did we learn? We learned bar charts, right? We didn't see pie charts yet because that's chapter 3. All right. And that's it for the review for section 4, chapter 1, which leads into today's things that we're going to talk about. All right. Any questions about that? All right. So let's see if I choose this one here. This is section 3, section 1. Yep, this is the one I want. All right. Actually, you didn't see that, so somebody's saying something with all right, somebody says they don't have the textbook yet. Yeah. All right. Well, you can talk to me after class about that. Send me your chat message about textbooks. All right. All right. So let's this is the one I chose. Let's share this one. Yeah. Yeah. This is probably it. Yeah. All right. Hopefully, give me a thumbs up. Dwayne, I could see your thing there. Can you see it? This is displaying categorical data. Do you see it on the screen? Good. Thank you. All right. So this is chapter 3, section 1. I'm going to try to get through first 2 sections, chapter 3 today, because section 3 might take a good portion of the next session that we have. And of course, we have a quiz also that we're going to be doing on Wednesday. So I'm going to try to cover these 2 sections today. And for the most part, this has to do with displaying mostly categorical data. Sections 3.1, categorical data only. Section 3.2 is numeric data, but it's only one type of plot, and I'll show you that pretty quickly. Now, I can tell you for the rest of the course, this section here, 3.1, you may see some questions on it, but not many, because this course will typically deal with numeric data sets more than categorical. However, it's really important for me to show you this section because many of you are not math majors and you're in other types of fields. You're probably going to see more of these types of charts. Bar charts and pie charts and things like that in your own readings, in your own field. So it's important that you see, at least understand what these charts are trying to do. So comparative bar charts, we looked at the bar chart before, again, for categorical data. And that's all they're used for, typically. Sometimes we want to compare 2 different groups that are measuring the same that have the same categories, and we just want to compare the distribution of counts between the 2 groups. All right, so you can use this to compare, or you can actually have more than 2 groups if you wanted to. All right, so here is a question. Do people with college degrees think that their education was worth the cost? So this is a questionnaire, right? So that's one of the questions that it's going to be asked. And also, one of the questions is going to be asked also is what type of college degree do you have? And some people are going to say associate degrees. Some people will say bachelor's degrees. I guess some people in the survey might have said also master's degrees or PhD, doctorate degrees. But they're only going to look in this particular comparison. We're only going to compare those people with associate degrees and those people with bachelor degrees. All right. Now the question is how many people are in each group? Now this is important to understand. So you look down at the total, and you notice that 2,548 in the study had associate degrees, but 30,151 had bachelor's degrees. So the groups are very uneven in terms of size, right? The associate degrees are much, much smaller group than the bachelor's degrees. So that's going to play a part in how we display our data. All right. So what are these numbers in here? These are the counts of people who answered that question. All right. So what was the question again? Do people with college degrees think that their education was worth the cost? There were 5 categories that a person would choose from. All right, so these categories were given. So strongly disagree. That means people didn't think it was worth it all. Waste of time. Disagree, maybe not as strong, but they still disagree with that statement. Maybe neither agree or disagree. That's people are kind of neutral. They didn't really agree or disagree with it. Some people moderately agree with it. Well, that's what they agree here. And then some people strongly agree with it, saying, yes, it was really worth it. And so there were how many people in the study? 30,151 with associate degrees, 2,548 who had, 30,151 had bachelor's degrees, 2,548 had associate degrees. So this question was asked to all these people, all of them. And so you have your frequencies over here. These are the counts. So 178 represents the number of associate degree holders who strongly disagreed with that statement. 1,508, for example, represent the number of people out of the 30,151 who strongly disagree with that statement. All right, so all the rest mean the same thing. Relative frequencies, basically, relative frequencies would be within each group, I think. Let me just make sure of that. No. So what they did here was the relative frequencies were the frequencies divided by the total number of people who were in the survey. All right, the total number, whatever that number is, and that's why they came up with these relative frequencies here. All right. Wait a minute. Let me make sure that's right. No, I'm sorry. So I'm incorrect. So let me rephrase what I just said. These relative frequencies are the proportion or percentage of people who were in that particular group who agreed or strongly disagreed. For example, there's 1,172 people who strongly agreed with that statement in the associate degree group, 2,548 total people in the associate degree group. 1,172 divided by 2,548 is approximately 0.46. So about 46% of the associate degree holders thought they strongly agreed with the statement that the college degree was worth it. All right, so yes, it's within each group. That's what these proportions are. Any questions about that? All right, and then it says here, because the two sample sizes are very different, it would be probably not fair to compare them with frequencies. What do I mean by that? Yeah. What if we just looked at frequencies over here and we compared the two groups? Now this color here, the peach color, I guess it's peach type color here, or tan color, is bachelor's degrees, and the lighter color here, the light, kind of very light green, is the associates. Now, if you were comparing frequencies here, you could think, oh, bachelor's degrees, just overwhelmed all the associate degrees in all these categories here. Well, this is an incorrect chart here because there were so many more people in the bachelor's group than the associate's group. This is unfair to compare these two groups. So what do? You do a percentage comparison. That would be a fair comparisons here. And now this makes a lot more sense, doesn't it? Some of the groups were favored in associate more in the associate group. Some of these categories, like for example here, there were a higher percentage of the associate degree holders who strongly disagreed than bachelor's degree. All right. It was the reverse here for agree. All right. More people in the bachelor's group, a higher percentage of people in the bachelor's group agreed with the statement than people in the associate's group. This is a higher bar here. And the scale here is proportion or percentage. All right, so this makes a lot more sense. All right, especially when you're comparing groups that have a very uneven number of counts. All right, you definitely want to compare the bar charts based off of relative frequencies, not off of frequencies. Any question about that? All right. So once again, for this course, if you see anything like this, maybe one question or so on the test on something like this, and then final exam you might see one question like this. So it's not going to be frequently tested on comparing, groups with bar charts, but it's something that you may see in your own field, or you may see bar charts that compare two different groups, like something like this. So be familiar with it and learn that it's better to make the comparison with relative frequencies along the y-axis here, because of especially if the groups are uneven in size. All right, and then you can make some determinations here. Since the response distributions are similar, let's look back, and they look pretty similar. So it says that both associate degree holders and bachelor degree holders generally agreed that education was worth the cost, right? And if you look back, yeah, greater percentage were in these two groups here, agree and strongly agree, right? Let's just take a look at the associate degree. It's like 40, looks like about 0.48 or something, like 48%. The associate degree were said strongly agree, and another 25 or 26% agree. So about over 70% agree or strongly agree, and the same thing is true for the bachelor's degree. So you just simply add up their relative frequencies, and you can see that most of them are over here. Well, you can also tell by the heights, right? The heights are much higher over here on the right than they are on the left. So people who agree there's many more people who agree than who disagree, or a greater percentage that agree than disagree. All right, so you can come to conclusions like that. All right, and this is common sense. There's nothing new here that you probably didn't already know. All right, and will I ask you to construct one of these things? Maybe in a homework or something like that, but not on a test. On a test, I would give you something like that, and then if it's multiple choice, I'm just going to give you some choices, and there will be something that will be true and something that will be false. That'll be pretty clear to see based on common sense. All right, and again, know that this way of displaying it is bad, incorrect, because we wouldn't use frequencies because of the two groups being such unequal size. All right. Now, and then the slide here is telling you the reason to do that. All right. Now, pie charts. Pie charts are also used for categorical data. So now we know bar charts are used for categorical data, and so are pie charts. I will never ask you to create a pie chart unless you had some software to be able to do it without making a mess. So you can use a pie chart, and the circle represents the whole data set. This makes sense. I think you sort of already know this. And then you have slices like a pizza pie, right? And the size of the slices are basically the relative frequency for that category. So the bigger the relative frequency, the bigger the slice that you see of the pie. All right, so let me show you an example right here. All right, so let's actually take a look at what they're asking here. All right, what's the survey? Each person surveyed was asked to select which of 5 fictional characters, Spider-Man, Batman, Fred Flintstone, Harry Potter, or Marge Simpson. Which of these 5, so you have to pick one of them, each person in the survey picked one of them, that you thought would have the greatest need for life insurance. Now, what is life insurance? It's insurance where you are basically insuring your life, and some other person, if you die, some other person gets some money. So obviously, people who are leading a so-called more risky life might have a higher chance of dying. So that's basically what they're asking here, I think. 1,014 adults were asked this question, and they had to choose one of these 4 fictional characters who they thought needed life insurance the most. And this is the result of the survey. Now, notice that they use a percentage. All right, here, percentage. This is the relative frequency, which is always expressed as a decimal, multiplied by 100 gives you the percentage. All right. So relative frequency times 100 gives you the percentage. So 12% is 0.12 if it's expressed as a relative frequency. All right, so these are all rounded, I guess, to the nearest percentage, whole percentage. So can somebody tell me which of these groups here, and they also had don't know is one of the answers. Which of these groups had the highest need based on the survey for life insurance? Which of these characters? Come on, guys. One of you must know this, unless you're not paying attention. Which of these, you can see what you're looking at. Which one of these has the greatest need, according to the survey?
Spider-Man.
Spider-Man, yeah. What percentage?
28.
28%, right. That's the largest percentage. That's the relative frequency. That's telling you that 28%, approximately 28% of the 1,000 or so people who were asked this question picked Spider-Man. Who was the second largest?
Batman.
Batman. Who was the smallest group? Smallest.
Marge Simpson.
Marge Simpson, right? Even the don't know category was bigger than Marge Simpson. All right. Although being married to Homer Simpson, I don't know why that maybe they life insurance is usually for married people. So it should have been either Fred Flintstone or Marge Simpson. Spider-Man, I don't believe, was married. So it's usually given. So anyway, it's just a comment. Anyway, so that was the assessment of people in the survey. And that's what a pie chart looks like. All right, categorical data. What are the categories? The names of the 1, 2, 3, 4. There was actually 5 people, 5 fictional characters, plus a 6th category of don't know. That was sort of a catch-all for people who didn't really have any idea. And that was those are the categories. So you show the categories, and then you show your percentages. And sometimes you'll see a key to the right here. You don't see the names here, but you see the color key. Each color represents a particular category. All right, so that's typically how a pie chart looks. And computer software typically is used for categorical data. Now, how are these percentages? How do you come up with these percentages, or how do you come up with the size of the slice? Well, if you go back to the chart here, if you remember your geometry, the total number of degrees around a circle is 360 degrees. That's true not only around the outer part of the circle, but around the inner part of the circle, around the center, is 360. So how do you come up with the size of these slices? It would be the percentage times 360 gives you this angle in here, the what's called an interior angle of the circle. All right. So that's why the slice is bigger if the percentage is bigger, because 20.28 times 360 gives you something around 100 degrees, I guess, 100 degrees, I believe, a little bit of around 100 degrees in terms of this angle in here. And that would be in the computer program actually calculates that and draws it for you. All right. But if you were going to use your, a tool like a protractor, you would be able to figure out what the angle is and draw it like this. But again, it's not something we would do in a statistics course, is actually draw a pie chart. But anyway, that's what they're explaining in this chart here. Now, do I ever ask a question like this? It's possible. This could be a multiple choice question regarding pie charts, how to calculate it. And just know that 360 degrees takes you all around the circle. And if you multiply the relative frequency times 360, that gives you the interior angle of that slice, and that tells you how big the slice of the pie is. All right, so typically, as it says here, we use statistical software. All the software packages do this. So if I give you a pie chart on a test, I would draw it for you using statistical software. Now, many times you will see something like this, where you compare different pie charts for different groups. So here we have two groups of people, scientists and non-scientists, who are asked if they agreed or disagree with the following statement. When something is run by government, it's usually inefficient and wasteful. Right? Do you agree or disagree? Well, what are the choices? Agree, disagree, and don't know are the three choices. So there will be three slices of the pie. And notice that if you look at the charts here, this is the scientist chart here, and this is the non-scientist. Somebody tell me, by looking at this chart, what's the big difference between scientists and non-scientists with regard to this question?
More scientists seem to disagree and non-scientists seem to agree.
That's right. That's exactly the conclusion, right? Because you can tell by the size of the pie, right? This size is the blue over here is bigger than the green. So more scientists disagree with that statement, and yet non-scientists tend to agree with the statement. There's more people who agree than disagree. Good, good. And that's all there is to this, right? There's, again, this is a type of chart that you would see typically in your field of study. Sometimes they show charts like this in the SATs, the quantitative part of the SATs, things like that. All right. Now you could also express this question in terms of comparative bar charts too. All right. You could do this also instead of having the pie chart, two pie charts, which might be a little bit difficult. And that one wasn't. That was easy to compare, but this is easier, isn't it? Where you have the categories running along the x-axis here. You have your relative frequencies along the y-axis, and then you have a key here where the green is the scientists, and this sort of brown color here, or maybe I don't know what color that is, sort of light brown color is the non-scientists. And now for each category, you can make a comparison, and you can see pretty clearly that more non-scientists agree than the scientists agree, and the more scientists would agree than non-scientists would disagree, right? Makes sense. And there's more non-scientists who don't know than there are scientists. That's another thing that you conclude from this. So this is another way of expressing the same chart. Is you could express it again as a comparative pie chart, or you can express it as a comparative bar chart. Okay, but again, categorical, because what's running along the x-axis here? Categories. You always will see categories running along the x-axis. Okay. see what else here. All right. Now, sometimes pie charts, sometimes, excuse me, let me rephrase it. Sometimes bar charts can look like a pie chart in a sense. It's not really look like a pie chart, but they're segmented just like pie charts are. So you could have bar charts that segmented. So what do they look like? Let me give you a chart here. Here's some categorical data here. Here's a frequency table. Here are your categories. These categories are based off of time, right? Basically, it says during the past year, how much time did you spend studying and doing homework in a typical week? Now, by the way, when the survey participant answers this question, they're going to give an exact amount of time, right? They're going to say 1 hour, 2 hours, 3 hours, whatever. How do they come up with these categories? Well, the researcher, there might be a research assistant. The researcher tells the research assistant, just count the number of people who gave an answer that's in this category, within this category. So anybody gave an answer of 2 hours or less, they're in category 1 here. Anybody gave an answer between 3 to 5 hours, that's category 2, like that. So these are your categories. There are 6 of them. And this happens to be your relative frequency. All right, relative frequency. So another way of expressing this would be to create something that looks like this. This is called a segmented bar chart. And some people like it to be displayed this way. And why would you do this? Well, maybe if you have so many categories, like 6 of them, it would be easier to have them all displayed in one bar. And the height of the bar is the height of the segment is the actual relative frequency. For example, here, if you look at the purple one here, the second one from the top, you can see that if you subtracted the relative frequency from the top of the bar to the bottom of the bar, it looks like about 0.1. So about 10% of the people picked between 16 and 20 hours. Okay. Out of these categories, which category had the largest relative frequency?
6 to 10 hours.
Yeah, 6, that's the green one, right? The green one. 6 to 10 hours, because the difference between the height of that segment and the bottom of that segment, the difference between these two is largest, right? It's larger than any other of these segments. You can see it. And so that would be the relative frequency for that. Now, again, computer software will do this for you. But this is one thing that is another way of just comparing categories when you have several categories. All right, this might be easier than just having the categories listed or along the x-axis, is to have them all segmented in this way. All right, so this is called a segmented bar chart. You can have segmented bar charts, and this is actually a nice one here, where you can have them for 2 different groups. All right, and this, what are the 2 groups? Well, first of all, the groups have to do with what? Amount of time spent on exercise or sports in a typical week. So they have the same categories in terms of the amount of time, all right? But one group is for people who do sports, and another group of people study. Now, for the people who exercise, what is the largest group for people who exercise? I mean, largest category for people who exercise?
2 hours or less, I think.
That's right. Right, now we're measuring the relative frequency along the x-axis. You see it? Along the x-axis as opposed to the y-axis. And we have our categories running along, not categories, but the groups running along the y-axis. So this is, again, is being used for display purposes, so you can see it. And for the study group, which one was the largest category? in terms of the number of hours studying.
6 to 10.
6 to 10. That's right. It's the widest segment here, isn't it? All right. So you get the idea how this works. You can compare. You can compare different groups and look at the distribution across categories, distribution of relative frequencies. That's pretty clever. And finally, one other use we're going to look at. We could have a pie chart that doesn't have frequencies anymore. Sometimes you have categories where you have you're not counting, you're measuring something. Now, it's still categorical because the chart is going to be displayed as categories. But now, instead of having you're counting the number of people, in this case you are measuring, in this case, the number of tons produced of what? Grapes, right? Grape production. We each have 4 different types of grapes. So here are 4 different types of grapes. Here's the tons of grapes that were produced in California in 2015 for each of these types of grapes. Total production in California for these 4 types of grapes. And you can display this as a pie chart. This is still considered categorical because what you're going to do is you're going to get your relative frequencies by dividing the production for each type of grape and divided by total production. All right. So the 2 million tons produced for red wine grapes divided by the 3.86 million total production gives you the relative frequency. Not relative frequency, you get your proportion. That would be the proportion of the total production that is for red wine grapes. All right. And those would be, so red wine obviously has the biggest percentage or proportion right here. You can see it, right? The next one would be white wine grapes, and the next one would be raisin, and the next one would be table, just by the size of the pie. All right. So this is another way of doing another application of a pie chart. All right. And here's another example where, again, you're not counting. You're in this case measuring, if you want to call it measuring, the amount of money that men and women typically spend for 5 different types of accessories. In a store, 5 different types of purchases: clothing, apartment furnishings, electronics and computers, school supplies, like that. All right, and shoes. So these are 5 categories, and we have 2 groups, men and women. You could picture us having maybe 2 pie charts comparing these 2. Again, you would have a total that you're taking the percentage of to get your proportions. But in this case, they're going to use what? They're going to use, and actually you're not going to use proportions in this case. You're going to actually use the actual amounts along the x-axis, and then you have your categories running along the y-axis, and you have your 2 groups, men and women. And the height for each of these rectangles is the average amount spent for each of these types of things that you purchase: clothing, furnishings, electronics, computers, school supplies, shoes, like that. All right, and you can make comparisons between the different groups. But this is considered a bar chart, and it's considered to be categorical because we're running categories running along the x-axis here. All right, so we're going to use a bar chart for them. Any questions about this section 3.1? Just a sort of a nice introduction to categorical data and looking at both bar charts and pie charts, many of which we were using comparative charts. Any questions about that? No? All right. So now we're going to go to the next section here, and it's on a quantitative data now. And let's see if let me see. This is in here. All right, so we just go right back to the top here. This is section 3.2. Now we're going to look at numerical data, and there's one that you probably never heard of before, even if you took statistics. You might not have heard of this. It's called stem and leaf displays. All right. And a stem and leaf display is a way of plotting numerical data. Now, can somebody tell me, we've learned it so far before this section here, we learned so far one graph or chart that we use for numerical data. Does anybody remember what that was from section 1.4? Now, by the way, this type of question I will ask on the final exam for sure. Maybe on test number 1, but for the final exam. Basically, which charts do we use for numerical? Which charts do we use for categorical? Anybody remember the chart we used at the beginning of today's session for numerical data? No? Dot plot. Dot plot. So this is the second one we're going to be learning about, stem and leaf. So dot plot and stem and leaf are used for numerical data. All right. Now, what we're going to do is we're going to take the numerical values in our data set and split them into pieces, where the first part of the number is going to be called the stem, typically the beginning digits of the numbers in your data set. And then the leaf is going to be the last part of each of the numbers in your data set, final digits. So we'll just do an example, show you what it looks like. Now, most likely I will, for stem and leaf questions on your test, and there will be one on your test and maybe one on your final. Typically, we'll give you a stem and leaf. I'm not going to ask you to create one, but I'll give you a stem and leaf, and I'm going to ask you questions about it. And some of the questions we haven't covered yet. We're going to be covering those in chapter 4. So some of these questions with stem and leaf we're going to hold off on until then. But anyway, here's an example here of splitting a number. For example, if you have the number 213 in a data set, you may have a couple different choices if you're going to create a stem and leaf in terms of what the stem would be. You may want to make the first digit, if it's all 3-digit numbers, you may want to make the first digit a 2, in this case, to be your stem, and then the 13 would be your leaf, or you can make the 21, the first 2 digits of the number, to be your stem, and the last digit to be your leaf. All right. Now you may ask, well, what's the point of doing this? Well, I'll show you in a second. So here's an example. The U.S. Department of Health and Human Services reported the estimated percentage of U.S. households with only wireless phone service, no landline, for the 50 states. All right. All right, and here are the results. All right, so here are 18 states and the District of Columbia are shown here. Not all the states. And here are the percentages of households that. Let me go back. Actually, what do you say? It's households with only wireless phone service, no landlines. Now, obviously, this is probably higher percentages now. All right. But anyway, here they are. And if we wanted to create a stem and leaf from this data, we would basically take a look at all the numbers in the data set and make a decision about what should be our stem and what should be the leaf. So, and the reason is basically what the stem and leaf is going to look like. Now, if we just use the first digit as our stem, so all the numbers here are 20s, 30s, and 40s, right? I believe they're all 20s, 30s, and 40s. So if you pick just the first digit, you would end up with 2 or 3 or 4 as your stem, and then the rest of the number would be displayed to your right. So for example, if you see 2, and then on the right you see 6.7, that is the number 26.7. 2 is the 2 part of the number is in the stem part, and they say it's tens, right? I mean, it's a tens digit. And then the ones digit, including the decimal, would be shown on the right. So 26.7 is a number in the data set, 29.4 is another number, 25.1 is a third number, 36.2, 31.5. You get the idea? It's just another way of displaying the numbers in your data set by creating the stems on the left, and then you have this vertical bar, and then you're listing on the right, you're listing the leaves, so-called leaves, which are the other piece of the numbers. You want to line them up so you see sort of a shape, sort of a shape of this distribution. Okay, and so that way you have the first three numbers are lined up exactly under each other, and then the rest of the numbers are lined up like that. In this case, they put commas in between the numbers because without the commas, you might get mixed up. You might be combining numbers here when you shouldn't be. If there were only whole numbers here, you could simply have spaces in between each of the numbers. All right, that's one way of displaying. But the problem with this is that there's only three categories, and that may not be enough. Excuse me, three stems, and you may want more stems. All right. So sometimes you may want to create another stem and leaf to see if it to see if it looks better. All right. All right. Now this one here, is this the same thing here? So you may want, again, this all has to do with constructing one of these things. I'm not going to ask you to construct the stem and leaf. I'm going to ask you to comment on the stem and leaf and make some calculations based off of it, which again, we won't be doing till starting next week. But I just want to show you what the stem and leaf looks like. It could look like that. We could also make it look another way. But the important point is it gives us some information. Now, what information does a stem and leaf give us? Well, it might give us information about an outlier. What's an outlier? An outlier is a value in the data set that's unusually small or unusually large. So it seems to be when we locate it on our stem and leaf, we may notice it's far away from most of the other data values. So it's a way of identifying an outlier. Now, why is that important? Well, number one, an outlier could indicate a mistake in recording the number in the data set. Sometimes that happens. Somebody typing it in makes a mistake. But if it's not a mistake, it would be something that we wanted to examine to understand why there's something unusually small, a value that's unusually small or unusually large in the data set. Now, stem and leaf typically are used strictly with small data sets because with larger data sets, it would get a little hard to see it. So we never use anything like this with large data sets. And if you take any other statistic classes in the future, you'll never use a stem and leaf. It's just typically used in introductory classes. All right. So again, they pretty much tell you how to create one, and also, and that's it. So this is instructions for doing it. Again, it's not something I'm going to ask you to do. And this is something important. What does a stem and leaf convey? So again, I give you a stem and leaf. You can do calculations. You can also do interpretations. And then interpretations could be one of these things here. It conveys information about a representative or typical value in the data set. In other words, where do most of the data values lie? So does it lie with smaller values, middle values, higher values, like that? How wide are these values? How variable are they? Are they very variable? Are they all close together? If there's any gaps or outliers in the data, it will show you with the stem and leaf. Also, we're going to talk next week, I think, more about this concept of symmetry in the data set. Does it look symmetric? Does it look skewed? That sort of thing, and a stem and leaf will give you that. And also about peaks. Do you have just one peak? Do you have multiple peaks? That sort of thing. Where are they located? Now, one advantage of stem and leaf, and if we go back, let's say pick another stem and leaf to look at here. Here's a data set, all right? And let me show you the stem and leaf for that, if they have one. There's one right here. I believe that's data set. And we'll go through this example in a second. But one of the advantages of a stem and leaf is that you can actually see the numbers in the data set. All right. Now on Wednesday, I'm going to show you a more common display for numerical data, and it's called a histogram. Now, histogram is used more often in statistics, but one of the things that it does not show are individual values. Typically, you don't see that in the histogram. With a stem and leaf, you can, and that's probably why introductory textbooks have stem and leaves, because you can actually take a look at a stem and leaf and actually enter all these numbers into your calculator, which I'll show you how to do on Wednesday. We're going to start using calculators. Hopefully you have your calculator, because we're starting it using your TI-8384 calculator Wednesday. So it's important to have it ready to go. But anyway, you can actually look at a stem and leaf, enter the numbers into your calculator, and then do statistics with them. All right, that's one of the big advantages of having a stem and leaf, and one of the reasons why I believe it's in an introductory class is that it has that feature. All right, so here is a data set here, and it's in your textbook, but it's data on average in-state tuition and fees of public institutions in the year 2016 for 50 US states. All right, and it's these are rounded to the nearest whole number. All right, so these are again 2016 public institutions tuition and fees. All right, you can see pretty low, right, for an in-state school compared to private schools, quite low. Notice it says here the observations range from a low of 4178 to a high of 15,062. Well, you'd have to scan the data set to find these numbers, and then I will show you with your calculator. Now, with your calculator, you don't have to do any scanning. It actually, your calculator will give you this information. So no more scanning that you'll need to do once you learn how to use your TI-83, TI-84 calculator. And one thing they recommended here, if you're going to create a stem and leaf from this data set, is to, because there are, let's see, 2, 4, 5 digits for many of these values, and 4 digits for others, they wanted all the numbers to be 5 digits. So they just put a 0 before the numbers that were 4 digits long. Just a prefix of a 0. All right. So that's why they did that, so that you could actually line up the numbers correctly when you plot them on a stem and leaf. Okay. So it says here a natural choice for the stem is the leading 2 digits. All right. And again, they run from, I see one, what's the smallest number in the data set again? It was 4178. So it would be run from around 40 up to 15. Excuse me, 4 up to 15, not 40, 4 up to 15 would be your stem, the first 2 digits. So 0, 4, 0, 5, all the way up to 15. So the first 2 digits would be the stem, and then the rest of the digits would be, of each number would be the leaf. All right. So again, that's what these are here. All right, so how would you read the numbers in this stem and leaf display? Well, the first number would be, the stem is 04 and the leaf is 438. So this would be 04, 438, or $4,438. All right. Second number would be 04,179. That's $4,179. All right. Let's go down here. Notice that there's no numbers in your data set that are $12,000 for tuition. But there is there's a couple in the data set that are 13,000. So 13 with a stem at 387. That particular state would have an average tuition of $13,387. All right. So the stems are in thousands, the leaves are in ones. All right. It's typically a key that tells you that. And then if you wanted, you could enter all of these 50 numbers into your calculator. I'll again show you how to do that on Wednesday, and then you can do various types of things like statistics. You can do a lot with it. So that's one of the things that I have people do on homework and also on a test is to, now I wouldn't give you a data set this big on a test, but I would give you one that you can enter pretty quickly, and then you can answer questions based on that. All right. Now, again, you could look at this and see that most of the values are between 6,000 and 9,000, right? Or maybe between $6,000 and $10,000 of tuition. Most of the states are in that category, and there are some that are state, the average state tuition is over 15,000, and there's others that are very cheap, right? 4,000, about 4,000. Most of them are in this middle part right here. Okay. Any questions about stem and leaf? One other thing I wanted to show you is that sometimes you can have, for the same stem, you can have repeats of the same stem being displayed. So let me see if I can find a stem and leaf. This goes over that with you. Well, here's a data set where this stem and leaf is kind of useless, right? There's only 3 categories. Now, each of these numbers, by the way, notice that the tens digits over here and the ones digits over here, and there's no commas. So here we have 29, we have 30, we have 32, 33, 34, like that. We have how many 40s? We have 6 numbers that are 40s in the data set. But there's not enough spread here between the different stems. So we might want to create additional stems here. How do we do it? We might want to create, let's say for the 30s here, we might want to create 30 low, 30 high. 30 low might be numbers in the 30s that run from 30 through 34. 30 highs would be ones that run from 35 all the way up to 39, like that. So you may want to, and you can see more of a spread between the numbers. All right. So sometimes you see an H and an L here representing the same stem, but broken up into more than one piece. And then you can use stem and leaf to compare. I'll show you what that looks like. Suppose you had these 2 countries here. You had North Africa. There's 19 countries in North Africa listed. And what are these numbers? They're percentage by primary school age children who were enrolled in school in North Africa. So these are percentages enrolled in school. You can see there's one country, North Africa, only have 34%. 34.3% enrolled in school. We want to compare it to Central Africa. All right. We want to do a comparison between these 2 groups. So we're going to use the same stem for both groups. So the stem actually runs down the middle here. And then the vertical bars here, you can see that on the right is North Africa. The leaves for North Africa on the right are the leaves for Central Africa. So, for example, for North Africa, we have, there's one country that's 34%. There's another country that's 48%. There's another country that has 54% and 59%. There's 2 countries there. None that have in the 60s for percentages. There's 2 countries, 77% and 76% in North Africa. Same thing in Central. We just read from right to left now. So 34%, 35%, 38%, 34%. There's 4 countries in Central Africa. 45%, 43%, 40%, like that. That's how you would read these. And then using the same stem, we can compare the distribution of the percentages. And you can see in North Africa, more of the percentages are toward the higher percentages. So North Africa, there are many more countries that have a high percentage of students that are enrolled in school, but not so much in Central Africa. There's more students that have a lower percentage of students that are enrolled in school. So the stem and leaf plays a nice role here in comparing these two groups, North Africa and Central Africa. All right, so that's another use for stem and leaf. So this is something, of course, I could also show you on a test or an interesting question. All right, any questions about stem and leaf displays? Again, used for quantitative data. So what did we learn today? We learned for quantitative data, two types of displays, dot plots and stem and leaf. And what did we learn for qualitative or categorical data? We learned pie charts and bar charts, okay? So that's what we learned today. And next time, we're going to learn a new type of chart, which will require use of your calculator. It's called a histogram, and we're going to use also how to create a frequency distribution for a quantitative variable. So histograms for a quantitative variable, and it will have a corresponding frequency distribution for the quantitative variable. All right, and we're going to learn how to do that next time. And then we have our quiz, which covers the first two chapters also next time. We'll do that in class. All right, any questions, comments? So it looks like our time is just about up. If you do have any personal questions, anything, do stay behind. That person who mentioned about your textbook, stay behind. All right, no questions? All right, so I'll stop the recording and I'll see you same time on Wednesday. All right. See you later.
Thank you.
Thank you.
Sure.
Thank you.
You too.